The Harlem River in 1895 was not a quiet waterway. Coal barges moved through it in convoys, riding low under their loads. Lumber schooners worked up from the East River toward the yards in the Bronx. Steam tugs pushed grain and oil and cinder scows north and south through the channel at all hours, and the captains of those vessels held federal navigation rights that no city engineer could override. Manhattan needed bridges across that river. The city pressed north at the rate of several new blocks a year, and the grid of Upper Manhattan stopped at the river's edge, while the Bronx began on the other side. The gap between them was a few hundred feet of tidal water. Building a fixed crossing would have strangled the river trade that kept those waterfront districts alive, so the city built movable bridges, swing bridges and bascule bridges, structures that could pivot or lift to open a navigation channel and then close again to carry road traffic. Between 1880 and 1910, the city constructed more than a dozen movable crossings over the Harlem River. The 3rd Avenue Bridge opened in 1898. The Willis Avenue Bridge opened in 1901. The original McCombs Dam Bridge was completed in 1895. Each one required building a foundation in a tidal river under active commercial navigation, setting a pivot mechanism precise enough to carry a span weighing several million pounds, and doing all of it while boat traffic passed on either side and street-level Manhattan continued underneath. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The men who built these bridges were not engineers drawing salaries at a city desk. They were ironworkers, sandhogs, masons, and riveting gangs who had come up through the elevated railroad lines being thrown across the city in the 1880s. Many of them were Irish, the sons of men who had worked the Croton Aqueduct and the railroads of the previous generation. Many were Italian, off the steamships from Naples and Calabria that were landing at the Battery in numbers that overwhelmed the processing stations at Castle Garden. They took the bridge work because it paid between $1 and $1.25 a day for general laborers and closer to $1.75 for skilled ironworkers, and because the city was expanding fast enough that there was always another job when the current one closed out. The same men who had riveted the 2nd Avenue Elevated and the 9th Avenue Elevated in the 1880s moved directly onto the bridge projects when those railroad contracts wound down. A journeyman ironworker in New York in the 1890s could work continuously for years without leaving the borough, following the steel from one structure to the next as the city built outward in every direction at once. The Harlem River added complications that a quieter channel would not have. The river was tidal, the current reversed twice a day, morning and afternoon, and a crew working inside a cofferdam at low tide was racing the return of the water at every session. The schedule for any temporary restriction of the navigation channel had to be cleared with the Army Corps of Engineers, which governed river traffic, and the operators whose coal barges moved through the draw were not patient when a bridge stayed closed longer than the permit allowed. The construction could not stop the river. It had to work around it. The problem with a swing bridge is that it is not a static structure. It is a machine. A swing span can weigh anywhere from 2 to 4 million pounds of steel, and it has to rotate on a central bearing to clear the navigation channel on one side and then rotate back to carry a loaded streetcar and the foot traffic of a city block on the other. The tolerance on the pivot mechanism is measured in fractions of an inch. A pier that settles unevenly by even a quarter inch across its base throws the bearing surface off plumb, and a bearing surface off plumb wears unevenly under the load cycling above it, and in 3 to 5 years, that wear shows in how the span rides when it opens and closes. The pier came first. For a swing bridge, the center pier is the machine base. It carries the entire load of the moving span on a single, perfectly level bearing surface set at its crown, and that pier has to be sunk in a tidal river in soil that the surveyors had probed but never fully trusted. The men who built the piers worked inside cofferdams. A cofferdam is a temporary watertight enclosure driven into the riverbed to hold the water back while construction happens inside. The cofferdams on the Harlem River bridges were built from interlocking timber or steel sheet piling driven into the river bottom with a steam-powered pile driver mounted on a work barge. The pile driver was a weight on a cable, lifted and dropped and lifted and dropped again, the sound of it carrying across the water and up into the streets of Washington Heights all day. When the piles were driven and sealed, the water inside was pumped out with steam-powered centrifugal pumps, and the men went in. The river bottom inside a pumped cofferdam is not clean earth. It is a combination of river silt, old timber from previous construction, broken stone, and discarded rope and chain and ballast from vessels going back a century, all of it compressed and waterlogged. The men who excavated it worked in standing water, even after pumping, because tidal seep through the pile joints replaced the water faster than the pumps could clear it. In summer, the mud smelled of everything the Harlem River had absorbed for 2 centuries. In winter, the men worked in cold that made the metal tools contract in the hand by mid-morning. There was no shelter in a cofferdam. You were in the river, just with the water temporarily held back. The foundation excavation went down until the men hit bedrock or a bearing stratum solid enough to take the load. On the Harlem River, bedrock lies at variable depth. In some sections it is 20 feet below the river bottom. In others it is 40 or 50 feet down, and the intervening material is sand, gravel, and soft clay that compresses under sustained load unless the pressure is spread across a wide footing. The engineers used concrete spread footings for piers on soft ground and cut to rock when the depth allowed it. Concrete in the 1890s was not the product it is today. The reliable hydraulic cements were primarily Rosendale cement from Ulster County and the early batches of Portland cement beginning to arrive from plants in New Jersey and Pennsylvania. Portland set harder and faster, but the masons who had worked with Rosendale on the aqueduct projects of the previous generation argued for the older material in every specification review they could get into. Once the footing was poured and cured, the pier walls went up. Coursed granite or dressed limestone, set in hydraulic mortar, built one course at a time from the river bottom to the waterline and above it. A pier for a swing bridge had to be built out to a round or elliptical profile at its base, so that ice moving down the river in spring breakup would be deflected rather than catching on a flat face. Flat-faced piers had been carried out by ice runs on the upper Hudson and the East River, often enough that nobody disputed the shape. At the top of the pier, the center bearing went in. The center bearing on a swing bridge from this era was a large cast-iron disc, machined flat to within a few thousandths of an inch, seated in mortar on the pier crown and leveled with more care than almost anything else on the job. A leveling error here could not be corrected after the span was in place. The men who set the bearing were not engineers. They were millwrights and ironworkers who had learned to read a spirit level and a surface plate and trusted their eyes as much as their instruments. The rim-bearing track, the outer ring the span rested on as it rotated, was set in the same pass. The track was a cast-iron ring, machined on its upper face, positioned a few feet out from the center on the pier masonry. Between the center pivot and the rim track, the span turned. The combined load of steel roadway, deck planking, overhead truss members, and live traffic moved on 2 contact points, the center pin and the rim bearing. Get either one wrong by 1/8 of an inch, and the span rocked in rotation. A span that rocked in rotation shed rivets. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The operators who ran these bridges worked in a small house at the center of the pivot pier, a brick or iron enclosure barely large enough for the steam engine and the levers and brake mechanisms that controlled speed and direction. A trained bridge tender could open a full swing span of 300 feet, from closed to full open in about 3.5 minutes. The navigation rules on the Harlem River required the bridge to be clear before a vessel reached the draw channel. A tender who held the bridge too long answered for it in the morning report. The riveting was the loudest part of the construction. A riveting gang on steel bridge work in 1900 was 4 men. The heater sat at a small coke-burning forge and brought rivets to temperature one at a time. When the rivet reached orange-yellow, what the men called a good heat, the heater pulled it with tongs and threw it to the catcher. The catcher was standing on the steel above, sometimes 30 or 40 feet up, and he caught the thrown rivet in a metal cone and drove it into the waiting hole. The bucker-up pressed an iron bar against the near end to hold the rivet in place. The driver put the hammer against the far end and drove the head down. 4 men, 1 rivet, 15 to 20 seconds on a clean run. The noise a riveting gang makes inside a steel box section is not a sound so much as a physical concussion, something you feel in your chest and your back teeth. The Harlem River bridge sites in the late 1890s had multiple riveting gangs working simultaneously on different parts of the same span. The men who drove rivets for years went partly or fully deaf, the way the tunnel drillers on the Croton Aqueduct line had gone deaf in the granite cuts at Yonkers 50 years before. The tools and the setting changed. The effect on the body did not. On jobs where the foundation depth required compressed air work, the danger took a different shape. When the soil under the river was too soft to work from inside a pumped cofferdam, the engineers used pneumatic caissons, enclosed chambers pressurized with compressed air to allow excavation at depth. The men inside those chambers breathed air at pressures above what the surface provides, and the nitrogen dissolved into their blood and tissue. When they ascended too fast, that nitrogen came back out of solution, forming bubbles in joints, in the spinal cord, in the vessels of the inner ear. The condition that river workers called caisson disease, which physicians later named decompression sickness, produced outcomes ranging from joint pain to paralysis. Some men came up bent double and never straightened properly again. The mechanism had been documented in the reports from the Brooklyn Bridge caisson work of the 1870s, where workers, including the supervising engineer, had been struck down by it. Slow decompression reduced the risk. But slow decompression cost time on a contract, and time was money, and the men going down were not in a position to negotiate the ascent rate with the contractor who held their weekly pay. The ironworkers who connected the steel overhead did the work without safety nets. There was no regulation requiring belts or lines in this era. A man working a truss connection 40 feet above the river deck held on, or he did not. When a catch failed, when a thrown rivet was missed, when the iron fell, it fell onto the men working below. Those incidents were noted in the manner of the era: name, date, cause, listed as fell from structure or struck by falling iron, wages settled to the last day of employment. Nothing beyond that. The Department of Bridges kept records of construction progress and inspection results for the Harlem River projects. The bridge inspection files are held in the New York City Municipal Archives. They note structural quality, masonry tolerances, bearing surface conditions, and span operation times. They do not record the names of the men who missed catches or came up wrong from the caissons or went deaf in the riveting gangs. Those names, when they survive, are scattered across contractor payroll ledgers and the parish registers of the churches the workers actually attended. St. Joseph's on East 125th Street served as the principal Irish Catholic parish for the Upper Manhattan construction workforce during this period. Our Lady of Mount Carmel on East 115th Street is where the Italian workers of East Harlem recorded their families. The neighborhoods that formed along the Bronx approach roads to the 3rd Avenue and Willis Avenue bridges grew directly from the foot traffic and streetcar lines those bridges made possible. The men who built the crossings generally did not stay long enough to benefit from what they built. They moved on to the next job when the current one paid out. The swing bridges of the Harlem River ran on steam until the city converted them to electric operation between 1910 and 1925. The electric motors were smaller, faster to start, and controllable with less physical effort. The operators who had worked the steam equipment said the electric bridges felt lighter in the hand. The lag between command and motion was shorter. The machinery forgave small errors in timing that the steam engines had not. The bridges themselves outlasted most of the systems that first moved them. The original McCombs Dam Bridge, completed in 1895, stood for more than a century before it was replaced in 2009. The 3rd Avenue Bridge of 1898 was replaced in 1995. The Willis Avenue Bridge followed in 2010. The steel of those original structures was melted, The foundations the Sandhogs had poured inside Cofferdams in the Harlem River mud are gone or buried beneath the new structures. What remains is less visible: the approach geometry of the streets, where the road grades rise to meet the old bridge deck elevations. In a few places along the Harlem River shoreline, cut stone from old approach walls still holds the fill behind it. Granite or limestone of a retaining structure built in the 1890s, still doing the job it was built for. The Harlem River still has movable bridges crossing it: the Broadway Bridge, the University Heights Bridge, the Spuyten-Duyvil Railroad Bridge at the northern end where the river meets the Hudson. Some of them still swing on center pier bearings set in the same era described here, repaired and reinforced but still turning on the geometry that pier masons leveled to within 1/8 of an inch in the 1890s. When a vessel comes through today and the tender opens the drawer and the span swings clear over the water, the motion is the motion those men designed. The mass of the steel, the turn of the bearing, the pause at full open while the vessel passes, the span closes, the traffic resumes, the river continues. What carries over from those original bridges is the physical fact of the crossing. The two banks joined, the road unbroken from Washington Heights to the Bronx, the same connection these men made in the mud of a tidal river for $1.25 a day. The men who made that possible are in the payroll ledgers and the parish registers, one name at a time, in ink that fades a little more each year. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.